Hi again, everyone. In this video, we're going to continue our investigation into ordinary differential equations. And last time, we gave a very basic introduction to the background, the motivation, and some of the applications of ordinary differential equations. So we talked about these ideas here, and we finished with what is a solution and a basic initial value problem. Okay, now in today's video, we're going to solve some first order ODEs, and in particular, we're going to look at a special class of differential equations called separable differential equations. Okay, so the first question is, what is a separable differential equation? Well, a separable differential equation basically has a special form. Okay, so in a nutshell, a separable differential equation is a differential equation that has two functions, in this case g and big H, multiplied together, and each of those functions is a function of x and y. So they're a function of one variable only. All right, so here you can see we've got a division going on. That's still a separable differential equation. Okay? All right, so how do we solve these things? Well, two basic steps. We separate the variables, and I'll say a little bit more about that as we do some examples. And then we integrate. We separate the variables, we integrate both sides of the equation, and then there's a little bit of cleaning up to do. All right, so let me give you an example of this separate and integrate type idea. All right. Solve the following differential equation. dy dx equals x times y. Now, you can see the right-hand side is a function of x times a function of y. So this is a separable ODE, separable ordinary differential equation. All right, so let's say f of x times g of y. And so it is separable. Okay, we separate the variables in the following way. So what I'm going to do here, I'm going to bring the dx up to the right-hand side and the y down the bottom to the left-hand side. So I get something a little like this. Okay, you can see I've broken up the dy dx to form a type of differential form here. All the y's and dy's are on one side, all the x's and dx's are on the other side. So this is what I mean by separating the variables. The next step is to integrate both sides. Okay, so I integrate here, integrate here. Now on the left-hand side, I'm integrating with respect to y. On the right-hand side, I'm integrating with respect to x. And so The left-hand side is going to give us log y, absolute. The right-hand side is going to give us a half x squared plus a constant. Okay, so we actually do have our solution there, y, in implicit form. What we would like to do is to rearrange this, make y the subject, remove those absolute value signs in some way. So let's have a look at this. The first thing I can do is remove the logarithm by taking the exponential of both sides. Okay, so I guess we're rearranging here, in a sense. So absolute y is going to be e to the half x squared plus this constant. What I would like to do now is to get rid of these absolute value signs. Okay? So what I'm going to do, I'm going to break up this right-hand side into e to the c times e to the half x squared. Now, just to make things a little bit more pretty, a little bit more convenient, what I can do is replace this plus or minus e to the constant by a new constant. Okay, say a. Now, this makes things a little cleaner and a little bit easier to work with. But there's one important thing that we've missed here. If you go back to your differential equation, you can easily verify that the zero function, y is identically equal to 0, is a solution to this. But if we go down to our solution, this can never be equal to 0 because this is positive and we have plus or minus some positive thing here. So this can never be equal to 0. So we've actually missed one of our solutions here. And I'm not sure if you know why, but it's all about dividing by y. When you make this division, we rule out the constant solution y equals 0. So we have to put that back in at some point. So we're still going to replace this with a new constant, but it must take into account the case y identically equal to 0. So we finally form the solution a times a half e to the x squared. Now this a here, you can think of it as a super constant. This a could be 0, or it could be plus or minus e to this integration constant. Okay? This is a nice, simple way of writing the solution that is easy to work with if we need to do things with it. Okay, so a equals constant. By that I mean it's 0 or plus or minus e to the c. Okay, now let's just look back here quickly and see how did I, why did I break up this dy dx? Can I do that and where did it come from? Well, I'm going to justify this very quickly, okay, just by rearranging the differential equation. Okay, so I'm going to justify that we can come up with this expression. All right, so I'm going to bring the y down here to form 1 on y dy dx. Equals x. Now, 1 on y is just the derivative of log y. Right? So I've just replaced this with d of log y dy. Now, what I can do is cancel off these dy's and I get dx here. d dx of log y equals x. Okay? So you can actually go to this step using the chain rule if you can see it. So all we need to do is to integrate both sides of this equation. So we integrate, we get log y equals a half x squared plus c. All right, so if we look back to our solution up here, this is exactly what we came up with. All right, but we didn't spend a lot of time messing around with this. We just separated the variables and integrated. Okay, but the justification for that is given down here. So when you do these problems, I suggest that you do it this way, but I'm just trying to convince you that that method is robust, it's well founded. Okay? All right. So here I've just given a more general idea of why the solution method works. Basically, the idea is to do exactly what I did at the second half of the previous problem, and you end up with this cancellation and integration, and then you have some sort of implicit form. Okay? All right, let's look at this particular problem. Solve this separable differential equation for x greater than 0. Okay? Now, we wouldn't expect the solution to this problem to exist at x equals 0 because the differential equation isn't defined at x equals 0. So we wouldn't expect a solution to exist there. The solution might exist for positive x and negative x, but not at x equals 0. Okay? The first thing we recognise is that our ODE is separable. So what do? We separate the variables and we integrate both sides. Thus we separate. Okay, so I'm going to bring that dx up there and that y squared down there. Next step, integrate both sides. Okay, so I'm integrating on the left-hand side with respect to y, and on the right-hand side with respect to x. So this is going to give us something like -1 on y, and this is going to give us something like log x. Okay, don't forget the constant of integration. Now, we can remove these absolute value signs because we know that we're only interested when x is positive. Okay? And secondly, I can clean this up a bit by writing this constant in another form. I'm going to write it as the log of another constant, k. Okay? And I'm just going to make the little note that k is positive, so this is defined. All right, now I can use my log laws to combine these into log kx. Again, this is just simplifying, and it'll be nice to work with if we need to do something with our function at the end. Okay, so what I would like to do now is to make y the subject. So I have y equals a function of x. So let's do that. So we rearrange to obtain the following. Okay, so y is going to be -1 on log kx, where k is a constant, and positive. All right, so this is the final form of the solution. Next question is, can we find this constant k And the answer is no, because we only have an ODE here. We don't have any extra information like an initial condition or something like this. Okay. Let's look at another problem. Solve the following initial value problem. Okay, so here's our ODE. Here's our extra piece of information. In other words, we know the value of the function, of the unknown function at one point, namely x equals 0. We know that the solution is equal to 1. And what we want to do is solve the whole, the combination of two equations here. All right, so our ODE is separable again. Remember, it's just a function of y times a function of x. So the idea is to separate the variables and integrate both sides. Okay, so we separate, so I'm going to bring that y squared down there and the dx up there. Right? And now I'm going to integrate both sides. Now, note here I'm integrating with respect to y. Over here I'm integrating with respect to x. Now on the left-hand side I'm going to get something like minus 1 on y. And on the right-hand side I'm going to get x plus a third x cubed plus a constant of integration. Now, what I would like to do is A, rearrange this and make y the subject, and B, find this constant of integration. I can do it because I have an initial condition. All right? So I'm going to rearrange first. To form this. Okay. Now let's apply the initial condition and find this C. So the initial condition is y of 0 equals 1. We obtain the following. All right, so I go up to here, I substitute in x equals 0, and I know the whole thing has to be equal to 1. So I'm going to get 0 there, and just C on the bottom. So if I rearrange this, C's got to be minus 1. So what I can do now is go back to my general solution, substitute C equals minus 1 in there, and I obtain my final answer. So y will be this function here. And of course I can check the function to see if it actually really is a solution by differentiating it and showing that A, this equation holds, and also the initial condition holds. All right, so here's a problem for you to try at home. We're given a so-called initial value problem. Okay, here the A, C, and D are just constants. Y is the unknown function, and we're asked to solve this initial value problem. And we're told that it arises in the analysis of rotationally symmetric bodies of smallest wave drag at hypersonic flow. Okay, now what you could do here is try to determine A, is the ODE actually separable? Can we use the methods that we've learnt today to solve this problem? And then if it is, go through and actually extract a solution. Well, let's answer the first question. Is this differential equation separable, where A is just a constant? And the answer is yes, because our ODE is separable as we can rearrange it. Okay, so how do we rearrange it? Well, the first thing I would do is take this y down here and then take the cubic root of both sides. All right, so we take the cubic root of both sides. So this is a separable differential equation. You would separate and integrate and then form the solution somehow. Okay, now the solution is given here. I'm not going to do that. I'm going to let you independently learn and formulate that solution. Okay, so good luck with it. All right, so the basic underlying principle of this video is A, see whether you have a separable differential equation in front of you. If you do, then you can separate the variables and integrate both sides and then rearrange and incorporate some sort of initial condition if necessary. Okay, now a good question here is what happens if the differential equation I'm looking at isn't separable? So, for example, how would you solve this? This is not a separable differential equation. So how do we solve it? Well, that's the subject of another video.